Hello students, this is Ashani from Cheenta.com. I hope you are doing beautiful mathematics. Today we will do a very nice problem from a very interesting competition. It's known as the Putnam contest. Putnam. It's a competition for college and university students, but many of the problems are very similar to math Olympiad problems for school students. For example, this problem says A, B, C and N are all positive integers. And we want to find out all the values of N. So find N such that there is a solution to this equation. These are sometimes known as Diophantine equation. There is a very interesting story about Diophantus. You can Google it or try to find it in the internet and learn more about it. These are essentially equations involving not all numbers but only integers. So the question is, for what values of n does this equation admit a solution? So for example, here is a problem solving strategy. Whenever we have a problem like this, we work with some particular cases. So let's write it down. Particular cases. Why do we work with particular cases? Because then our brain sort of picks up on the pattern, and then the brain can then generalize what's going on. So it's always a great idea to try your hand in some specific situations. For example, n equals to 1. What happens when n is equal to 1? Well, we have 2a plus 3b equal to 4c. Are there solutions, integer solutions to this equation? Well, in fact, you can do this very quickly by inspection. A equals to 1, B equals to 2, C equals to 2 is one solution to this equation, because 2 plus 6 is equals to 8. Now, there might be other solutions as well. In fact, here is a side question, like a challenge problem. A challenge. Can you find out all solutions? Maybe you can find a form of the solutions of this equation. Integer solutions, by the way. Okay, now that we understand this, let's try with the case n equals to 2. N equals to 1 is done. The next question is, what happens with n equals to 2? We are slowly building on this so that we can comment on a general value of n. Okay, so the equation is 2a square plus 3b square is equal to 4c square. So whenever I see a Diophantine equation like this, one of the things that I do is something known as a square residue check. What is a square residue check? Well, a square residue check is basically looking at square numbers and thinking about what remainders can they produce when divided by, let's say, 3. So if I have a square quantity, what is it congruent to modulo 3? I hope you are familiar with modular arithmetic. If you are not, you can check the YouTube channel that we have. There are plenty of videos on modular arithmetic. So in other words, if I have a random number x, if I square it, what remainders can it produce when divided by 3? And you can easily check this. Any number x is congruent to either 0, 1 or 2 modulo 3. Obviously, these are the three possible remainders, 0, 1, 2. If I divide any number by 3, these are the possible remainders. Now we can square them and check what's happening. 0 square is obviously 0 modulo 3. 1 square is 1 modulo 3. 2 square is 4, which is 1 modulo 3. So what we just found is that any square number produces either 0 or 1 as the remainder. This is a very powerful information about square numbers. We can use this to solve interesting problems. Let's look at this equation one more time. 3a square plus 2a square plus 3b square equal to 4c square. So, let me write it one more time. 2a square plus 3b square equal to 4c square. I will add a square to both sides. And I will subtract a 3c square from both sides. Essentially, I'm trying to make a multiple of 3 on one side of the equation. And that's exactly what I have. I have 3 times a square plus b square minus c square on the left hand side. And on the right hand side, I have a square plus c square. So, this equation tells me that the left hand side is divisible by 3, or it's 0 mod 3. So since the right hand side is equal to the left hand side, therefore the right hand side must be also equal to 0 mod 3. That's wonderful, isn't it? How simply we could find out that a quantity is divisible by 3. Now there is something very interesting about two square numbers getting added up to 0 mod 3. And what is that? Well, each of them must be 0 mod 3. Why? Because what are the other possibilities? Can both of them be 1? Well, 1 plus 1 is 2 mod 3, which is not 0 mod 3. Both of them cannot be 1 mod 3. Is it possible that one of them is 1 mod 3 and the other one is 0 mod 3? Well, if you add 1 and 0, you get 1. But you want a square plus c square to be congruent to 0 mod 3. So both of them cannot be 1 mod 3. One of them is 1 mod 3, one of them is 0 mod 3. That's also not possible. So what is the other thing that's possible? Both of them are 0 mod 3. So what we essentially have is a square is congruent to 0 mod 3, c square is congruent to 0 mod 3, which means 3 divides a, 3 divides c. We are at the very end of this particular solution. Why? Because, notice, whenever we have an equation like this is a very common strategy. You can assume that the GCD of ABC is 1. Why? Because if something was, let's say D was the GCD, we could have cancelled it off from both sides. Right? So if D divides the left hand side and D divides the right hand side, then we can cancel it off from both sides. So we can assume that ABC has GCD 1. Okay? And we just now found that A and C are divisible by 3. So let's say I write A equals to 3A1 and C equals to 3C1. Okay, now let's write the equation one more time. 2A square is 2 times 3A1 square plus 3B square equals to 4 times 3C1 whole square. Okay, so 2 times 9A1 square plus 3B square equals to 4 times 9C1 square. I can cancel by 3 on both sides. So I have 3 times 2, 6A1 square plus B square equal to 3 times 4, 12C1 square. Let's bring everything to one side. B square equals to 12C1 square minus 6A1 square. I can take a 3 common again. So 4C1 square minus 2A1 square. So B square is now divisible by 3. B square is divisible by 3. So which means B is divisible by 3. A square is divisible by a prime number only if the number itself is divisible by the prime number, and 3 is a prime number. So we found that 3 divides B as well. Wow. That means we found 3 divides all 3 of them, A, B, C. But how can that be possible? Because we just assumed that the GCD of ABC is 1. So we found a contradiction. So this is basically the contradiction. Therefore, there is no solution to the equation 2a square plus 3b square equal to 4c square. Okay, so now I will give you as a challenge the cube and the 4th power and the 5th power case, all of the other cases. It's actually very similar. Here is a challenge. Try the other powers and put it in the comment section if you have a solution. We checked it using modulo 3. Here, for the other powers, you have to check it with modulo 2 or modulo 2 to the power something. That's the hint, okay? I hope you learned something. If you are interested in mathematical Olympiads, in ISI, CMI entrances, in research in school and college and universities, then you can check the link in the description. I think we have some wonderful programs for you, and you will probably like them. Take care. Bye.